Hi guys, Miss McQuaid here. So I'm going to do your very first video lecture. So I'm going to just explain some things, watch, follow along, and answer the questions on your guided notes packet. This homework will be checked, and we're going to do this throughout the year, so hopefully you get it. Very cool. So right here, what I have is a sample of copper, and we are zooming in, and I'm going to zoom in even further. So I'm zooming in on this sample, this piece of copper. Now, each of these spheres is an atom of copper. Now, what we call this is a particle diagram or a particle view. The idea is that all matter, no matter what it is, if you zoomed in all the way, you could see the individual atoms or particles that make up this substance. All right, so what I'm going to do with my simulation here is, first of all, I'm going to move myself over a little bit. Move myself up here. Okay, I'll sit up here. So what we see here are the particles of copper. Now over here in my bar, I can change the temperature in the simulation. And when I change the temperature, temperature is a measurement of the kinetic energy of a sample. Kinetic energy is the energy of motion. So when I increase the temperature, I'm going to make the particles move faster. Now watch. They're going to move faster and bump into each other more often. I'm going to go back. Oh, there we go. To my outside view. So here we go. I'm going to go back down. Now, you'll see here that the particles, although they are moving, they're not moving from one place to another place. Instead, they're vibrating in one place. And we call that place a fixed position. So the particles are in a fixed geometric pattern. And although I can move the box, you can see that the particle can vibrate in place, but not move from one place to another place. So solid particles are tightly packed together. As I increase the temperature, you will see that the particles start to move faster. And as the particles move faster, they bump into each other more often, and we call that a collision. All right, so the particles are colliding more often. They are still in the solid phase. Eventually, they're going to have enough energy to move from one place to another. And when the particles of a solid move further apart and can now move from one place to another, we now have a liquid. The name of the phase change from a solid to a liquid is called melting. So this represents the particles that have melted from a solid into a liquid. Now in a liquid, the particles can move from place to place, but they're still very close together. So we say that a liquid will take the shape of the container. The particles can flow past each other. Now if I continue to increase the temperature, I get the particles to move very far apart. And now I have particles of a gas. Now notice that the particles of a gas are colliding more often, and they have more kinetic energy. So the most kinetic energy exists in a gas. Now the particles can move from place to place, and they move in a random straight line pattern. So let me show you what I mean by random straight line pattern. So I'm going to go ahead and do show trajectory. Now it's kind of hard to see because we're following one atom, but I'm going to go here and click on run slowly so you can see this same thing with the same amount of kinetic energy in slow-mo. Now watch in slow motion as we follow this one particle. It is moving in a random straight line motion. So it's going to move in a straight line until it bumps into another molecule, and then it can bounce off. So they're moving in constant, random, straight line motion. Now notice the kinetic energy of the sample is what we call the average kinetic energy. I'm going to go ahead and click off of the slow-mo, and I'm going to undo the trajectory. Oh, I can't undo the trajectory. All right. I wonder what would happen if we changed something other than temperature. So I'm going to go ahead and change my temperature back down to medium temperature. So here we have a liquid and some particles escaping into a gas. Now what would happen if I changed the interatomic attraction? So what would happen if I made the atoms less sticky, less attracted to each other? They would spread out more. So the weaker the intermolecular forces, the more spread out the particles will be. Go back to my medium amount. There's my liquid. Now make a prediction. What do you think will happen if I increase the force of attraction? There we go. The particles are now acting like a solid, even though I did not change the temperature. Now this would be changing the substance itself, because this factor is determined by the type of atom that we have here. We could also change the type of atom by changing how heavy the atom is, how massive the atom is. Notice I have very light atoms here. Think about it. What would happen if I made the atoms very heavy? Would it take more energy to push them apart, or less energy to push them apart? I'm going to go ahead and make the atoms heavier. Notice that when I make the atoms more massive, they're more stuck together. It takes more energy to separate heavier atoms than it would take to separate lighter atoms. So to recap, at the lowest temperature and having medium of everything else, we have a solid. Without changing any other factors, if I increase the temperature, solid particles will move further apart and become a liquid. That phase change is called melting. Now I have a liquid. The particles are still close together, but they can move from place to place. Now, if I continue to increase the temperature, we can see that the particles become a gas. And going from a liquid to a gas is called vaporization. When energy is absorbed, the particles can move further apart and spread out and move from place to place. So the particles of a solid are closest together, then a liquid are at medium distance, and the furthest apart are particles of a gas. Right? That's all for today. Hope you enjoyed my particle diagrams and this demonstration.